Okay, my friends, this is Roger, Mudfossil University, and when I had young kids, and I used to say to them every now and then, I'd say, listen to me, this is my serious voice. And I'm telling you right now, listen to me, this is my serious voice. You see that right there? This is Yellowstone. They've got dozens of earthquakes are popping up there, a little more than normal. Now, let's discuss why and what is the possibilities here. Now, in my last video, I discussed, and I know it was very hard to hear, it was about the underground activity in the Italian provinces there that are you know, I believe it's Mount Etna and Vesuvius and all of that stuff that erupted at one point in time. And it's so hot under that surface right now, and these two guys, Rob Nelson and Stephen Burns, and they have a channel called Secrets of the Underground, and they go and they explore this, and I'd like them to do this here and see what they find, because under Naples it's over boiling, which means that the water is now turning to vapor, because you cannot exceed 212 degrees and continue to have condensed water molecules. They turn into vapor, which is expansive, and they found all of this stuff. I'm not making anything up. Everything I'm talking about, they found it in spades. Now let's talk about Yellowstone. All right, you just saw Yellowstone. Well, listen to what Tyson has to say here, and then he's going to show you what he has to show you.
Okay, you're going to see this scene in my video. And that there is a valve. I believe totally 100% now.
You see that? It's a vein valve.
And here's the arterial side. Now I'm going to show you something else.
All right, you see it?
Unless anybody can prove this is volcanic.
All right, now, well, if you got one of these, you're probably going to have one of the arteries. All right, here's Tyson again. Now, don't forget, all of these caves, as he contacted all the biologists, I mean the geologists out there, and those are all volcanic. We know exactly what they are, and they refuse to talk with them. Now, watch this. You saw what I consider to be a vein valve, and so does Tyson. And now what about this? Let's see what we have here.
As you can see, I got my light on here to get more light in here. But you notice these caves, these walls are nothing like lava tubes whatsoever. And then I got this valving, this big plug back in here. I'll get the light closer. Grab this light.
That's arterial blood. All right, whenever you see red blood, or red, that's FeO3. It's got an extra oxygen. You see it? I don't think too many lava tubes look like that. And when he got up real close and looked at it, you could see there's little bits of black blood in there too. Because there's this black and red blood together, but primarily in the artery, it's 99% red blood. And then these are just the walls of the artery. And they solidify in different colors, depends on, you know, the conditions they're in. It's just the way it works. I don't know what else to say other than it's time to look at this with a little opener eyes. Because when you look at what we are showing you here, this is what you're seeing at Yellowstone, only it's under duress. All right, that's what they think is some kind of volcanic fumarole. Well, what that is, more than likely, is it's some form of a body tube going into the body. Now, whether it's an anus or it's a blood supply, vein or artery, or whether it's part of the lungs, or whether it's going through the kidney, because you see, you're going to have all different kinds of chemistry. The reason they find all these different sulfuric this and bubbling that is because your body does this. That's what your body does. It makes this kind of chemistry. So depends on what area they're looking at, what kind of chemistry is flowing out of there, you can make some kind of a determination what kind of body part you're dealing with. And there's so much to know about this, and it's really not that complicated. And you know, and there's not much you can do about it, although you can plan. And that's all I'm saying. I'm not, you know, oh, this guy's going to scare everybody. Well, maybe they're going to get scared. But if this was going to explode, I'd be scared if I lived right over there. I'd want to know, what can I tell? What is the temperature? Because I'm going to tell you what, I've been studying temperature deeply because of electron flood theory, which replaces the Bohr model, which is destroyed. They know it's destroyed. It doesn't work. It hasn't worked for years. And electron flood says there's nothing more than electrons. And when you put too many of them in, you end up getting explosiveness, which is what's called the ultraviolet catastrophe. And I will show you that. And that's in light. When you get into matter, you get into the water catastrophe, where is it above 212, it becomes vapor. And then if it's compacted, it is nowhere for it to go. Now you got issues. You see that, my friends? That is where the blood drains down, probably into the foot, and then it runs off into the other blood vessels down there. Now, what happens is specific gravity, in certain cases, not all the time, but it will end up leaving a little plug of gold at the spot where it is filtered out, basically. And here's another one now. Now sometimes they'll, like this one here, turn into silver. See the blood right there? This is where the blood filtered out. If you look, you can see that's bone right there. There's a little tiny bit of bone left, and that's basically it. The rest is turned, I think mostly this is silver. It's in that range, in this range of the periodic chart, because that's the density of that metals, those metals, and then they filter out being, you know, sort of backed up. And that is a gold toe, and that's where the blood comes. And here's a toe right here, or a finger, or I think this is a finger, but that's where the blood is here. And you can see, you see that? That's blood. You see that? That is blood right there, blood. And that is really what is this right here. Whoops, it's upside down. But that's it right there. And this, everything drained out, and it kept the blood back. And I'm sure that was the plug right there that kept everything back. You could see the blood vessels, and you could see it's either, you know, the bone, or you could see the blood vessels, and you could see the blood in all of these lumps of gold, flakes and so forth, where you don't see it. Well, let me show you something else. Okay, inside the body, there's all kinds of veins and arteries, and some of them purge, and some of them get plugged. Well, this is blood, and this is gold. And apparently, this was probably at an angle something like this, and the gold was filtered out at the bottom and just backed up according to specific gravity. That's all I can say. Okay, now, if you know me and been following me at all, you understand I am deep into chemistry, and transition metals are one of my absolute favorites. And this chick right here is unbelievable. And she is going to talk about transition metals in blood. And that's what gives them their colors. Because here's the deal. Transition metals sit right in the middle of a bunch of electrons this way and a bunch of electrons that way. You got both sides of the periodic chart, and they're right in the middle, so they can give and take. Now, that's why you have colors. That's why you get all these different colors, and that's why they're so totally necessary in biology. And she understands that. This is just fabulous. This is MIT, and it's free. This is free. 2.48 million subscribers. Listen to this.
All right, so moving to today's handout. This is one of my favorite parts of the course. Honestly, when I first started teaching 5.11.1, I said, transition metals are rarely covered in intro chemistry courses. Is it really necessary to cover it here? And I was told it absolutely was. It's one of the reasons that a 5 on the AP exam is not good enough, that you have to take the advanced standing exam, because the people who teach inorganic chemistry found that people who placed out of 5.11.1 didn't do as well in their course as people who took 5.11.1 here. So this is one of the reasons. And then I started teaching it and I realized this is one of the, even though people haven't seen it before and sometimes people get a little scared, it's actually one of the most fun units. So I absolutely love it, and hopefully you will love it by the end. People are like, we never covered it, why are you covering it? We're in chapter 16.
Before she goes any further, I just want to say one thing. I am going to go through this whole thing very deeply, because electron flood theory says there is no protons and neutrons in the core. The core is nothing more than a ton of particles, which we would call electrons, which is a non-explosive particle and an extremely explosive particle. The extremely explosive we call negative, the non-explosive we call positive, but they are dipole and they have to stay together until they explode. Then the black one can just roll off, and I show this in our experiments, and I will just before we start. But the red ones, they don't want to be, they push each other apart, but they have to stay with their black ones. So they end up creating a core at a certain resonance frequency, and that is helium right there. That's just the tiniest core and 2 electrons. All right, I'm going to do this like rocket ship fast. Pulse red laser, accelerating pulse red laser because of a Venturi. The particle that exists within inside the pulse red laser pulling out. Higgs fields coming this way at us, interacting with the particles that are in the air. This nobody knows about. It looks like it's an antiparticle concussing with a regular particle, creating a who knows what. This is what particles look like, photons. They are basically like this as they come through, and they have positive, negative all around in a box, and that makes them spin because they smack into the concussive parts. Now, let's see, and they do spin. You can see easily that they spin, and they accelerate. That is also easily seen. You see this? That's a spin to the right, which means it drifts to the left. You see how open it is here and how concussed it is here? That is the nature of light, which is not understood now whatsoever. Now, this shows that the red and black, remember I showed you those particles in the box? There's the little black parts walking away. You see the black parts? And they can get right up next to each other. They don't have any concussion against each other, or very little. But the white ones, they just explode like a bomb. You see the little black ones? They walk away. This was the part coming through here, spinning like crazy. And when it interacted, the black ones just got thrown off, and the white ones are fighting each other, creating this enormous energy field. All right, now before we go any further, let's just take isotopes. And this is isotopes of palladium, because it's in the middle. Okay, so it's got a little give and take. Now, what does it say about a naturally occurring palladium is composed of 6 stable isotopes? What does that mean? These are the number of what they think are protons, that type of thing, that are in there. Theoretically unstable 110. Now, but you go down to where they are actually finding isotopes. Look, this is the whole list of isotopes. All palladium. So it's not just one particle, and then you go up to silver, and then cadmium and so forth. It can have all of these variations. This is the issue. They just forget about it, don't worry about it. Well, how could it have all of that stuff and only be these gigantic protons and neutrons? It's not that way. It's 100% particles in the core. And now I'm starting to try to understand how the core is really constructed when you get up beyond the very basic. Because once you get from the basic s orbitals into the p orbitals, where you get into what they call the rule of 8, something changes. Now, is there a central positiveness surrounded by a negativeness which has to be attached to the positives because they are dipoles, and then start another row into the nucleus? I think it must be. I'm trying to put it together, but when you look at it in the salt vibration experiments, it's extremely interesting because these particles, they actually create the web of bubbles. And they lock in at a certain frequency, it becomes a certain atom. And then another 1,000 cycles, it's just in chaos, and then bam, it locks in again at another elegant looking. Well, let's look at it real quick. But this, we really got to look at electron flood theory to go with reality, because otherwise they're just walking around in circles. The same thing with geology. You got to look at reality. Reality is reality. I don't care if they told you, oh, read this book. It's not right. If it's not right, it's not right. Okay, I've been meaning to get into this anyway, so I'm gonna go real deep into chemistry, where you're gonna understand everything about chemistry, because it's not that hard. All right, you just got to open your mind up and say, let me just think and relax. All right, she is very good. Listen to this now.
It's fun. Okay, so transition metals, D-block metals, because they have those d orbitals. Yes, we're going back to talking about orbitals again. And they're called transition metals because you transition from this part of the periodic table with your what kind of orbitals? S, to this part of your periodic table with your what kind of orbitals? P. So they are the transition metals. And they're often really reactive and very cool.
They're very reactive because they are in the middle of the periodic chart. Again, they can give and take. That's what reactivity is. And salt is extremely NaCl. There's a ton of things can happen in between.
And many of them, since we're on a biological theme, many of them are super important in biology. And I have some of these written down in your notes. But
now, as you saw, my claim is that those colored substances coming out of these fumaroles and these sulfur pools and so forth are biology from organs, literally.
But here they are. Up here in the transition metals, you have a lot of metals that we could not live without. Iron carries oxygen to our blood, very important. Hemoglobin. We talked about cobalt just now. That is the metal in vitamin B12, so we know why that's important. We have zinc everywhere.
Just so you understand, all these metals have what they call as ligands, which is a little pinch that they can pinch with a single little electron and carry something through the blood to a point where another place says, hey, I got an extra electron, can I have that? And they say, yeah, here, you take it and give me that. And they hand off, and that's the delivery system. So that's why they are so reactive, and that's why they are so important in the body chemistry, and that's why they come out of these fumaroles.
Nickel's important for bacteria, not so much for us, but bacteria is important for us, so therefore nickel's important to us. So all of these are really important. Also, this part of the periodic table is part of the table that people love that want to make pharmaceuticals or want to make new kinds of electrodes or batteries or all sorts of things. There's a bunch that are used as probes. We talked about imaging agents detecting cancer and all sorts of different things like that. Many of these transition metals are used in those probes. And
how they use them in these probes is they look for molecular attachments to certain molecules. All right? Every molecule that is reactive will react a certain way to, like, if it comes head on, it'll attach. If it goes like this, it won't. It's that type of thing, simple as that. And that's how these electrons interact with each other. Now, I'm still working on the nucleus part and how easy it is to change the nucleus. I don't think it's very easy, because once you get into nuclear radiation, the nucleus is broken and smashed into bits and pieces. And now you got to put it back together. I think you might be able to do it with ultrasonic vibrations, because that's exactly how the salt table works. And I'm telling you, this is nothing more than salt when it's in its nuclear explosive state. Let's look at that.